Good evening, everyone, and thank you for joining us this late in the day. So both me and Maria, as were introduced, are focused on how the collective space is evolving, and we will share some of those insights and also what we are adding into ROCm comms library space. If you look back a few years, AI training was simple. Your model would fit into a GPU. You have large amount of data that you would chunk and feed it across several GPUs. Periodically, you had to sync the gradients, and that meant that all reduce was the dominant collective and message sizes were typically large. More recently, models have grown in size and complexity. And to help address this, the community has developed tensor parallelism, with which it brings the need to support latency-sensitive small message all reduce. We have also seen introduction of pipeline parallelism, where various layers of models are sharded across different GPUs. And with it comes the need to move data across these layers in an assembly line fashion. What does this mean? It means that point-to-point communications will be predominant. In addition to all these, we have also seen introduction of mixture of experts or expert parallelism. With this comes the need to route tokens to a dynamic set in an all-to-all fashion. And any training that you see in real world today doesn't employ one of these techniques. You will see all of them. Within a node, you will see tensor parallelism. Across groups of nodes, you will see pipeline parallelism. Across sets of these groups, you would see data parallelism and mixture of experts laying on the top. And what does this mean for collectives? It means that collectives need to be topology aware, schedule aware, should be able to support various demands in terms of latency tolerance and message sizes. Let's take a few more minutes to look at what applications would look like. First up, inference. As we all can agree, latency is critical here. It impacts the user experience. And the compute kernels are typically short-lived. And there is a need to launch communication right after compute kernels are done. And we see two trends here. One, fusing compute and comms together, eliminating the need to involve CPUs or the need to do any setup. The second trend we see is use of symmetric memories, where the need to have staging buffers is eliminated, and a GPU can write into any other GPU's HBM directly. Let's spend a minute on training too. Training, which typically runs across several days and months, efficiency is the focus. The models lend themselves for us to think about compute and comms overlap. While the GPUs are busy crunching gradients, say for layer I of compute, we can trigger all reduce for the previous layer. And training typically runs on tens of thousands of GPUs, with which comes some unique challenges. And we'll touch on 3 of them. When these GPUs use the same network fabric, congestion is imminent. You need the capability to route across congestion hotspots. Next, the amount of time it takes to bootstrap a job, which could have been in few seconds for small scale, will turn out to be tens of seconds, if not minutes. And you pay this penalty every time a job needs to restart. Third is the resources that collectives themselves will consume and maybe store your computation workloads. In terms of memory on HBM and Q pairs, you need to optimize for this. To help us address some of these challenges, we have introduced several features in both NIXL and rocSHMEM, and my colleague here, Maria, will help introduce a subset of these.
Thanks, Shashi, for the introduction. Next, we will highlight key innovations in AMD communication runtime, NIXL and rocSHMEM to address these critical application needs. Let's first start with NIXL. NIXL is the AMD collective communication library. So Shashi talked about applications overlap compute and communication. To support that case, we have enabled the use of copy engines. We call it system DMA, so SDMA, to move data across GPUs. Enabling SDMA is important because what we do is we offload the data transfer to the SDMA so that the compute units are fully available to the computation, to the matrix multiplication. What we enable is better overlap and that results on higher speedups. Let me show you the data. So here, what is the pointer? Yeah. So here we have two plots. In the first plot, what we have is the time of either a gem or an all-gather running on isolation. For the all-gather, we have the different message sizes, and we have two bars. The first bar corresponds to the time of the all-gather using the compute units. The next bar corresponds to the time of the all-gather using the SDMA. These two bars have about the same height. That's not the important thing. The important thing is the impact when the all-gather running with the SDMA together with the gem has on the overall time of the application. That is shown on this plot here. So on this plot here, what we have is a speed up when running together an all-gather with the SDMA and the gem versus the case where we are using the all-gather implemented with the compute units. Okay? So, so on the x-axis, what we have is the gem running together with an all-gather of different sizes. You can see if the size of the all-gather is small or the size of the all-gather is big, meaning it takes either little time or a lot of time, there is almost no impact on the execution time or on the speedup. However, when the time of the all-gather is about the same as the matrix-matrix multiplication, you can see that we can have a significant speedup when the all-gather is using the SDMA. The reason is that we are using the resources more efficiently. We are letting the gem use the compute units, and we are using the SDMA to move the data across GPUs. So that is a better use of the resources and better overlap. Sassy was talking also how important is small meshes for inference. In inference, if you think about that, every microsecond matters. Every microsecond is time that the user has to wait for the data to complete. It's actually money also that is going to cost more. We understand that, and we have invested on reducing the latency of the small messages, both for single node and for multiple nodes. So let's focus first on single node. We know the ring algorithm is not good for small and medium messages. So we have invested on other algorithms like one shot or two shots. These ones can perform the collective in either one step or two steps. We support both cases, register and unregistered buffer. The registered buffer, you heard Sassy talk about the symmetric memory. We enable through the symmetric memory. That requires application changes. There is a new API that is window register. We actually support both cases. When the application registers the memory, even if the framework doesn't change, we can also support that. Let me show you the impact of that. So in this figure, what we have is a speed up with respect to the default algorithm in recall, which is usually a ring, except in the case of the all-to-all, for the different collectives. In the x-axis, what you have is the message sizes, and what you can see is that in all the cases, we have significant speed up. This is for both cases, when we register the buffer and when we don't register the buffer. The highest speed up is achieved in all reduce, is 3.7. You can see there is some difference between the time for the unregistered and registered buffer. That's because we are still missing some optimizations. We are working on that. We are going to improve those times. And this, by the way, will run on a single node, 8 GPUs, MI350. We have also working on reducing the latency for multiple nodes. The current algorithms in recall are not optimal. I'm not going to go into the details. What we've done is we implemented a hierarchical algorithm that is topology aware. The way it works, if you take an all-gather, when you are communicating across multiple nodes, you could think we use a structure that we call communicator. We split that into two parts. One is what we call the scale-out. And so those are the ranks, the similar ranks that are communicating across nodes. And for that, we can use for all-gather what we call the path algorithm, which is optimized for low latency. And then in the intracom, that's basically what we call the scale-up communicator. These are the GPUs within the node. There we can use any algorithm, but we can use the ones that we have presented before, the one node and the one shot and the two shots. Let me show you the results. So what we have here in this plot is the speed up. In this case, we are running an all-gather, 16 nodes. Each node is 8 GPUs, MI350. Again, the x-axis, what you have is the message size. And here, what you have is the speed up of the hierarchical algorithm. This is the new one that I was talking about with respect to the default algorithm in recall. You can see that we have a speed up of up to 3.6 GPU, 3.6. If we continue with inference, what we know is that in inference it's very difficult to overlap compute and communication. The communication usually appears on the critical path. Communication is always overhead. So what we have invested is to provide mechanisms so that the application can fuse the compute and the communication in the same kernel, because that's the way to overlap. So we enable GPU-initiated communication, both scale-up and scale-out. For the scale-up, we do that through regular load stores that will consume compute units. But we have also enabled the use of the SDMA, initiating that from the kernel. That's actually a novelty. And that's important because we can do a data transfer initiating from the kernel using a single CU, single compute unit. We also support GPU-initiated communication for a scale-out. Our optimized path is using GPU-direct async, initiating for the kernel. And we support 3 different NICs. Obviously, the AMD Pensando Polara NIC. We are also enabling the next generation, the Volcano, the Broadcom Thor X, and the Connect 7. Let me show you some results. So in this plot, what we are showing is the bus bandwidth for an all-to-all. These results are run on a single node, 8 GPUs MI355. And what we are showing on the y-axis is the bus bandwidth. On the x-axis, what you have is the message size. I have 2 bars here. One is the recall default algorithm. This is the red bar. That is using CUs, and it can use up to 64 compute units. And then the blue bar is the one that is initiated from the GPU, and is using the SDMA. That one is using a single CU. You can see that if the messages are on the medium size, the recall default algorithm is a little bit better. Once the messages grow in size, the SDMA is actually better than the recall default. But what is important is that we are achieving either similar performance or higher using a single CU. Okay? The other one, the recall default, is using up to 64 CUs. If we are running at the same time a matrix-matrix multiplication or a compute, we are leaving all the other resources for the matrix-matrix multiplication. And as before, that will be a higher speed up. We also enable GPU-initiated communication for a scale-out. So in this case, we are running experiments. We are showing data for, I think it's 4 nodes running on MI300. This is the bus bandwidth for an all-to-all. In this case, we are running in 4 nodes. The scale-up is using what we call the load and store. So basically, we'll be consuming CUs. And for the scale-out, we are using the GPU-direct async. So this is bus bandwidth. The x-axis have the message sizes, and I have the bus bandwidth of the all-to-all. So the first bar, the red one, is the recall default algorithm, and the green one is actually the GPU initiated bar. You can see that in this case, for 16 megabytes, we are having higher bandwidth. This technique is important for inference, and in inference, the messages tend to be smaller. So this plot is also showing the latency in microseconds. You can see the latency of the recall default algorithm, and with GPU-initiated communication, we are able to push down that latency significantly. Congestion. So we also have to support training applications. Training applications run at a large scale. When you run at a large scale, you are going to have congestion. So the data centers using the ROCm v2 protocol for routing, and there is a strategy called ECMP, equal cost multiple path, that is used to split the traffic across multiple paths. But this strategy uses a hash function. That hash function can result in collisions. And you have here an example. You have 2 flows. And the hash function can be such that both flows end up using the same link, when in reality we have here another link that could have been used for the traffic, so that these 2 flows could have been running concurrently. So we have added support for that. The support that we have added is actually an extension of the current mechanism that exists in recall. In recall, between a given source and destination, we have multiple queue pairs, And what we do is we distribute the traffic either round robin, different messages are sent through different QPs, or either splitting. If the message is large, we split it. So on top of that, we added what we call CAST, congestion-aware spray traffic. Basically, the idea is that we collect information about the round trip, and we use that information to dynamically distribute the load. We can either do a weighted split or a weighted distribution. You see here, for instance, imagine that I have multiple messages. What I do is, through that QP that is more congested, I'm going to send fewer messages. And I know that because I am actually measuring the round trips through the different QPs. So the QP that has the highest round trip time is the one that will be more congested. OK, what is the impact of that? So we are going to show that in an all-to-all. In this case, we are running an all-to-all between two nodes. Each node has MI355, 8 MI355. We selected these two nodes so that they are not connected to the same switch. So they have to go through a spine switch so that we can have multiple paths. So what we are showing in this plot is the bandwidth ratio, and the x-axis, what I have, is the message size. For each message size, I have 3 bars. The first one is the time of the all-to-all, but I have a background noise in order to create the congestion, OK? So that is my reference. The gray bar is the ideal case, is the bandwidth ratio of the all-to-all, assuming that we do not have any of this background noise. And then the bar in the middle, which is kind of a dark blue, is the time when we apply our strategy, the CAS. And you can see that in all the cases, we are bringing the bandwidth very close to the optimal, and we are able to achieve a speed up to 1.7. No, this is really a pure software technique. So what we are doing is we are measuring the time, the round trip of the completions. And with that, we distribute the traffic through the multiple QPs. We already have that support for the multiple QPs. We in software can distribute the traffic. Yep. Yep. So I'm going to talk a little bit about rocSHMEM. rocSHMEM is our GPU-initiated runtime that implements the OpenSHMEM APIs. So we've done something similar to what we've done for Recall. We have added support in rocSHMEM to be able to start from the GPU data transfer with the SDMA. And the outcome is very similar to what we saw on Recall. So here you have the time of an all-to-all running on 8 MI355. So we have a speed up with respect of the input size. So the speed up here is computed an all-to-all running on rocSHMEM using SDMA, so it will use only a single CU, versus the default Recall. Okay? The data are basically very similar. If the messages are relatively small, they both behave about the same. You can see that the speed up is around 1. But again, we are using only with the SDMA, we use a single CU. If the messages are larger, the bandwidth is higher, up to 35 higher. Again, the Recall default algorithm is using 64 CUs. With this one, we can use only a single CU. This plot is just showing some performance data. So rocSHMEM is a GPU-initiated runtime. So what we are showing here is the bus bandwidth of a benchmark doing a non-blocking put. So in this case, what we have are 2 GPUs on different nodes. We have to run this experiment 3 times because I'm showing results for 3 different NICs. These are the 3 types of NICs that we support: the Pollara NIC, the Thor NIC, and the Connect7. So the plot shows the plot shows the bus bandwidth for the different message sizes. What you can see is that we are able to achieve peak bandwidth for all the 3 NICs. These NICs will have 50 gigabytes per second. You never achieve exactly 50, but very close, about 64. We achieve about the same point for all of them. It's a GPU-initiated communication, so we are really trying to get good latency. You have that here. So this is the latency for at 8 bytes, and you can see the values are actually very competitive for these NICs. Okay? This concludes our presentation. I have to have a disclaimer because I have performance data. There is much more coming. and we really would love the feedback. Thank you for coming. Yeah.
I think we can take the questions offline. There's a next talk schedule. We'll be hanging out in the area. Thank you.